This is the video presentation for the 418 Animation Systems module. We'll start off by showcasing the 2D animation system. This is currently playing the frame-based animation, and this can be switched by pressing the keys that are displayed on the user interface. So now I can switch to a moving animation, standing, jumping and running, and an attack animation. I can switch between frame-based and skeleton-based animation by pressing S. So once I press S, the skeletal-based animation appears. And different animations can also be played the same method by pressing the displayed keys. And here are the different animations. The system can be switched back and forth through the sprite-based and the skeletal-based, and by pressing the spacebar I can switch between the 2D and 3D animation systems. This is currently playing a 2D blended animation between a standard idle and happy idle, as well as standard walking and happy walking, and this can be controlled by the arrow keys. So currently if I increase the happiness, you'll notice the character's head kind of bobs up and the character moves around a bit more. And by increasing the speed, the character starts walking, and currently it is playing a happy walk, and if I reduce the happiness, it can slow down to a standard walk. And by reducing the walking speed, I can go back to the regular idle animation, and this can be controlled throughout. You can switch to running. This performs a smooth transition. The user interface is currently displaying the state which is played. So we can switch to a dance which is performing a frozen transition, switch to another dance also performing a frozen transition, and I can switch back and forth to animations. Going back to the 2D blend initially, it stops running, and I can continue to control the 2D blend. By pressing I can move to inverse kinematics. Here the mouse button can be clicked down to control where the arm is moving. Inverse kinematics is currently working only on these angles. As soon as it goes under the shoulder, there is a bug. Moving on to the UML diagram of the 2D animation system. The 2D animation system contains a 2D animated character instance. This class contains the sprite object and the necessary functions for rendering and updating the animated sprite. This class contains 4 components, which are the bone class instance, the skin slot instance, and an animation data instance, as well as a texture atlas instance. The animation data class handles the reading of animation data from the JSON file, the updating of animations, and switching between animations. It also contains the structures that are used for storing the animation data read from the JSON file. The texture atlas class loads in the texture atlas data and the subtextures. Bone and skin slot classes are used to store the loaded bones and skin slot data, as well as calculating the required transforms. Moving on to the UML diagram of the 3D system, the animated character class is used for updating and rendering the animated skin mesh. The animation state manager handles the current state of the character and how it should be animated. This class specifies how and when transitions between animations should happen. The animation control class contains the blend tree and handles the transitions and blending between the animations based on the state. The animation control class contains instances of a blend tree, animation data, clip node, and 2-dimensional blend node classes. The blend node class represents a single node in the blend tree and is parent to several types of nodes, which are each responsible for transitions and playing animation clips. The blend tree class is used to go through its nodes and perform the required computations for producing the blended animations. The animation system's design is modeled to follow an object-oriented approach. More specifically, the principle of composition over inheritance is used for the entire 2D system and most of the 3D system, except for the blend tree classes, which use inheritance. The functionality of the different parts of the animation system is obtained by putting together components that are not specifically related to each other, such as the loading of animation data and controlling the animation being played. This is a good approach as each component can focus on its specific tasks, making class hierarchy more manageable and increasing the readability of the code. An object-oriented approach is used as, according to the following study, it increases the cohesion of the system and reduces the complexity. So for example, in the 3D animation system, the animation control class deals with the blending of the animation, and the animation data class deals with the loading of animation clips, which are both separate parts of the 3D animation system. To decrease the memory usage, only one system is initialized at the time, meaning that only the files required for the current system are in memory. The main drawback is that when one system is switched to the other, all the data required for the new system is loaded. Due to the small amount of animation files and their respective sizes, there is no noticeable decrease in performance, however. The application only updates the current system it is showcasing, so either 2D or 3D. This is done for performance, as it would be computationally expensive to update and handle inputs for both systems when only one is being showcased. In the 3D system, the blend tree only updates the nodes that are required for the current state. When transitions are complete, the output node is set to the clip node of the current state. The only exception in this case would be the 3D blend animation, which uses 4 clip nodes. So instead of having all the clips and nodes updating, it only updates the required ones based on the current state. The 2D system has a single 2D character class which contains the functionality to update and render both types of animations, key pose and frame-based. The animation data class is used to contain the data necessary for animation. This is a functional architecture, but its main drawback is that the 2D character class contains all the functionality for both frame-based animations and key pose-based animations, which could lead to confusion. It would be better if there were 2 different classes, each representing the 2 different types of 2D animated characters. This would also increase the reusability of the code. Adding more flexibility would be good, being able to specify the assets when initializing the 2D character. The software architecture of the 3D system is structured by 2 layers, the animation pipeline and the animation state manager. The animation pipeline is formed by the classes that are responsible for playing loaded animation clips, blending the clips, and producing skeletal pose as output for rendering. The animation state manager controls which clips are being played and the transitions between these clips. This is a commonly used architecture throughout animation systems, and the use of an animation state manager provides a higher level intuitive system for controlling the animations. One of the main limitations of the 3D system is the large number of classes, which makes it hard to navigate the code base and could make the code less understandable. This also increases the use of memory. This limitation could be solved by moving the blend nodes for transitions into a single file, or creating a single blend node which can perform different types of transitions. The functionality of the motion clip player class, which is used to display a clip, could be added into the clip node class. Another limitation is that the inverse kinematics is not integrated into the blend tree system. Partial skeleton blending refers to the technique of blending animations on a character or object by selectively blending only certain bones or joints of the skeleton, rather than blending the entire skeleton. This allows for more precise control over the animation and can create more natural and believable movement. Currently, the 3D system applies the same blend factor for the entire skeleton. To implement partial skeletal blending, the skeleton pose class could be extended so that the blend factors could be applied to specified joints of the skeleton. Definitions for the joints that compose different body parts, such as the upper torso or the legs, would have to be created. Then, the blend nodes would have to be updated so that the part of the skeleton being blended is specified. Through the use of a neural network, character animations that match and adjust the surrounding geometry can be created. The system takes in user controls and the geometry surrounding the character and the current state of the character, and it produces motion such as walking on a rough terrain. The neural network is trained using a large dataset that contains different types of motion, such as walking, jumping, or crouching in different geometric environments. One of the problems for adapting this technique to real-time applications is that the produced motion can look stiff and artificial at places, and it is hard to generate a stylized animation. This could be fixed by adding a layer on top of the neural network that deals with animations where the neural network struggles, such as small variations in the terrain or complex environments. Finally, here are the references to the resources that were used for creating this project.